My name is Ian Mospa, and my project is the effect of Bluff body profile on the prevention of vortex shedding by a splitter plate. Flow past a Bluff body is an area of fluid mechanics which has been studied at great length. Generally, the Reynolds number, as shown in equation 1, dictates the behavior of a flow. The Reynolds number is a dimensionless number which compares the velocity u of the fluid and the characteristic diameter d of the Bluff body to the kinematic viscosity v, or nu, of the fluid in motion. At very low Reynolds numbers less than 5, flows are laminar with no flow separation. At Reynolds numbers greater than 5, a pair of vortices begin to form downstream of the body and attach to the body. With increasing Reynolds numbers, usually between 45 and 150, the vortices increase in size until a critical point is reached, and instability in the flow causes one of the vortices to detach from the Bluff body. The detached vortex will travel downstream as a new vortex is formed to take its place, still attached to the Bluff body. Likewise, the other attached vortex will at some point separate from the Bluff body and travel downstream before a new vortex is formed to take its place. The shedding of the vortex pairs will continue to occur and will do so at a predictable frequency. Vortex shedding is sometimes also referred to as Kármán vortex streets. Given that vortices represent regions of high velocity and low pressure, periodic vortex shedding can induce alternating areas of high and low pressure on the downstream face of the Bluff body. Thereby, periodic vortex shedding induces alternating lift and drag forces transverse and parallel to the flow, respectively. These forces can cause a detriment to the performance of a system, for example, a plane's aerofoil or a jet engine's stators, or oscillatory motion in a structure such as a building or chimney. Therefore, a great deal of research has been conducted into methods of preventing periodic vortex shedding. Chief among these methods is a so-called splitter plate, which is attached to the downstream side of the Bluff body and bisects the flow. The splitter plate prevents the vortices from interacting and thus prevents instabilities in the region between the vortices from destabilizing each vortex. In this manner, the splitter plate prevents periodic vortex shedding from occurring. A variety of studies have investigated the effectiveness of splitter plates under a number of parameters. These include the length, width, and profile of the splitter plate, the Reynolds number within the laminar vortex street regime, between 45 and 150, and cross-sectional profile of the Bluff body. Commonly, circular or square cross-sections are used for the Bluff body. Less commonly, an isosceles triangle is used for the cross-section. While each of these profiles have been investigated by previous research, a direct comparison of the three profiles does not appear to have been conducted. This is especially true within an isosceles triangular section. Therefore, this project aimed to directly compare the three profiles and their effects on splitter plate effectiveness. The goal of this project was to directly compare the effectiveness of a splitter plate and the prevention of periodic vortex shedding when affixed to a cylinder of circular, square, or isosceles triangular cross-section. To this end, computational fluid dynamic simulations of the three cross-sections were created and solved using the free and open source solver OpenFOAM version 18.6. These models were generated as two-dimensional, incompressible, laminar, transient flows. These simulations were solved using pisofoam with a single free-stream velocity, Bluff body characteristic diameter, and kinematic viscosity. Therefore, the simulations were solved using the same Reynolds number. In this case, Reynolds number equals 100. This value was chosen as it represents an average of the laminar vortex shedding regime between 45 and 150, as shown in Figure 1. The ratio of length to characteristic diameter, L over D, of the splitter plate was modulated to determine at which length periodic vortex shedding ceased. The critical splitter plate L over D of each cross-section was then compared. The effect of the splitter plate and body profile on vortex shedding, period, and frequency was also analyzed. Kármán vortex streets can be mathematically modeled via the complex potential. Given an infinite number of vortices with a span-wise center-to-center distance of A and a stream-wise center-to-center distance of B, the complex potential is given in equation 2, where W, the complex potential, equals negative I times gamma, the circulation, divided by 2 pi times log of the sine of pi z over A. The derivative of equation 2 gives the complex velocity at a point z in the flow field, given in equation 4. The derivative of equation 2 gives the complex velocity at a point z in the flow field, equation 3. dw dz equals negative I times gamma divided by 2 pi times the cotangent of pi z over A. Equation 4 gives the velocity of a vortex street as a whole. The velocity v equals gamma over 2 pi times the tangent of pi b over A. While Kármán vortex streets can be modeled, it is not possible to solve for the street analytically and must be determined experimentally or numerically. The Struve-Hall number, abbreviated as ST, is a dimensionless number used to analyze flows which exhibit unsteady oscillatory behavior, as given in equation 5. The Struve-Hall number compares frequency, F, of the vortex shedding multiplied by the characteristic diameter of the Bluff body, d, to the free stream velocity of the flow, u. Through empirical methods, the Struve-Hall number has been fit to equation 6, giving St as a function of Reynolds number. By combining these equations, the frequency can be isolated from the rest of the equation, as given in equation 7, and thus calculated only from the values of u, d, and nu. Given that the models were solved using a Reynolds number of 100, a vortex shedding frequency of 0.158994 Hz, and a period of 6.29 seconds is expected. 2 baseline models were generated to represent the 3 cross-section profiles. One model, Mod 1, was generated to represent the circle and square cross-sections, and a second model, Mod 2, represented the isosceles triangle cross-section. These models were two-dimensional, with the front and back faces being defined as empty in OpenFOAM. Mod 1 consists of 13 regions defined by 48 vertices. Region 0 represents the non-wetted volume inside the cylinder and the splitter plate. Regions 1 through 3 lie in front of the Bluff body and act as the upstream domain. Regions 4 and 5 lie below and above the Bluff body. Regions 6 through 12 lie downstream of the body, with regions 7 through 8 directly downstream of the body and adjacent to either side of the splitter plate. Mod 2 consists of 12 regions defined by 44 vertices. Region 0 represents the non-wetted volume inside the cylinder and the splitter plate. Regions 1 through 2 lie in front of the Bluff body and act as the upstream domain. Regions 3 and 4 lie above and below the Bluff body. Regions 5 through 12 lie downstream of the body, with regions 6 and 7 directly downstream of the body and adjacent to either side of the splitter plate. The cylinder of square cross-section used in Mod 1 was given a length of 1 meter on each edge. When Mod 1 was used to simulate the flow around a cylinder of circular cross-section, the edges of the Bluff body were changed from lines to arcs, giving the circle a diameter of 1 meter. In Mod 2, the isosceles triangle was given a width and a height of 1 meter. In all cases, the upstreammost points of the Bluff bodies lie at x equals 0 meters, and the downstreammost points lie at x equals 1 meter. In all cases, the splitter plate was modeled as 1 centimeter thick, with a length of 0, 0.5, 1, 1.5, 2, 2.5, 3, or 4 meters. When compared to the free stream velocity of 1 meters per second, this gave a dimensionless length and height of 1, a splitter plate thickness of 0.1, and a splitter plate length and diameter of 0 through 4. In this case, the length over diameter is the length of the splitter plate divided by the characteristic diameter of the Bluff body, which is 1. A convergence study of the domain size was conducted to ensure the domain was sufficiently large and that the boundary conditions did impose realistic conditions on the flow. The final domain size was defined as 50 meters by 100 meters, with the longer dimension aligned with the flow. The domain extended 25 meters upstream from the Bluff body and 75 meters downstream. Likewise, the domain extended 25 meters above and below the body. The mesh in both Mod 1 and Mod 2 were modulated in order to find a balance between accuracy and runtime. In both mods, the final mesh contained 147,000 elements. This number was selected through a mesh convergence study between 70,000 and 550,000 elements. A mesh size of 147,000 elements was found to be the smallest number of elements at which the solution was stable and did not change as the number of elements increased. On average, the mesh contained 300 elements along the vertical axis and 500 along the horizontal axis. This led to 15 to 30 elements being generated along each of the bluff body faces and splitter plate faces. The mesh used a structured grid and consisted only of 2D quadrangular elements. The mesh was defined such that the elements were clustered around the bluff body and the axis of symmetry. The mesh bias was defined so that the elements at the boundaries were 3 to 10 times the size of the elements on the bluff body. Once the mesh was generated, boundary and initial conditions were assigned to the model. For definitions of pressure, all boundaries were set to 0 gradient except for the downstream boundary, which was set to a uniform fixed value of 0. For the definitions of velocity, the boundaries on the bluff body and splitter plate were set to a uniform fixed value of 0. The upper and lower wall were set to slip conditions. The inlet was set to a uniform fixed value of 1 meter per second. In all cases, the front and back were set to empty to give a 2D solution. The outlet velocity was set to 0 gradient. The simulation turbulence properties were set to laminar. For turbulence properties, the pisofoam solver requires only kinematic viscosity, which was set to 0.01 meters squared per second. The generated models were solved using OpenFOAM version 18.06. The selected solver model was pisofoam, which is an incompressible and transient solver. Pisofoam makes use of the pressure implicit with splitting of operators or PISO algorithm. The residual tolerances for pressure and velocity were set to 1 times 10 to the minus 6th and 1 times 10 to the minus 8th, respectively. Mod 2 was solved at a time step of 0.025 seconds, while Mod 1 was solved at a time step of 0.02 for the square profile and 0.0125 for the circular profile. These time steps provided good convergence of the results and a coherent number of less than 1.0. Across the models, the average of the mean coherent time was approximately 0.1, and the average maximum coherent number was approximately 0.85. The coherent number is a measure of how long a particle remains within a given element. If the coherent number is greater than 1, it means the particle travels through an entire cell and can effectively skip over it in a single time step. This can lead to divergence of the solution or the solver missing some of the features of the flow. The time step scheme was set to Euler, and the divergence gradient and Laplacian schemes were set to Gauss linear. The interpolation schemes were set to linear. The relaxation factors for pressure and velocity were set to 0.3 and 0.7 respectively. The pressure and velocity solvers were set to PCG/DIC and smooth solver/Gauss-Seidel respectively. The control dict file set the solution to write every 40 to 80 iterations, giving a data file every 1 second of flow time. All simulations were run for a total of 250 to 420 seconds of flow time. The control dict also printed out pressure at 4 probe points at every time step. The probe points were defined as 10 meters and 25 meters downstream of the bluff body, and 10 meters and 25 meters and 0.5 meters above the bluff body, with coordinates given in meters. Once the simulations had been solved, the resulting data was post-processed. The simulations were primarily post-processed through Microsoft Excel and the visualization tool Parafoam. Parafoam was used to visually inspect the results and identify trends in the flow behavior. In particular, Parafoam was used to identify at what splitter plate L/D ratio vortex shedding ceased. The pressure probe data was post-processed using Excel. The last 4,096 time steps of each flow of each model was analyzed using a fast Fourier or FFT transform. The FFT provided the frequency that each of the probe points experienced pressure fluctuations. The dominant frequency of pressure fluctuations of the probe points on the center line of the domain were approximately double the frequency of those off the center line. Conversely, the frequency of the 2 points on the center line were almost identical. Therefore, the probe points on the center line of the flow were used. This frequency was then compared to the predicted frequency as given previously. Excel was also used to compare the amplitude of the pressure fluctuations across the models to determine the relationship between amplitude and therefore vortex strength and splitter plate size. After the data was post-processed, the results were collated in order to identify trends in the data. These figures show the evolution of pressure contours of a circular cylinder over time. As discussed previously, the flow starts stable with vortices growing behind the Bluff body. By approximately 50 seconds, the flow has destabilized and periodic vortex shedding has begun. As the flow progresses, vortex shedding continues until a Kármán vortex street has developed. In flows with longer splitter plates, the vortices remain attached to the Bluff body and no Kármán vortex street develops. These general behaviors are reflected by the square and triangular cylinders as well. Here we can see the pressure contours of flow around cylinders of circular cross-section. Here we can see the pressure contours of flow around cylinders of square cross-section. Here we can see the pressure contours of flow around cylinders of triangular cross-section. This figure shows the pressure versus time history of the 4 pressure probe points for a circular cylinder with no splitter plate. The latter section of the time history of the probe points on the center line was isolated for post-processing as shown in this figure. A fast Fourier transform was used to convert this data into a frequency histogram, as shown here. In cases where periodic vortex shedding occurred, a clean dominant frequency was present. The data from the pressure probe at 10 meters downstream was then selected to be further analyzed. From the time histories of each case, the amplitude of the pressure fluctuations, as well as the minimum pressure found in the developed flow, were recorded. These figures plot the amplitude and magnitude of the pressures as a function of splitter plate, L over D, and Bluff body profile. Here we can see the period of vortex shedding as a function of splitter plate L over D. These results demonstrate a strong influence of Bluff body profile on splitter plate effectiveness. As shown in this figure, the amplitude of pressure fluctuations downstream of the Bluff body slowly becomes smaller as splitter plate L over D increases. The exception is that for the triangular profile, the fluctuation amplitude is actually smaller at an L over D of 0 than 0.5. For the circular profile, the amplitude is only very slightly less at 0 L over D than 0.5 L over D. As splitter plate L over D increases, a point is reached where the amplitude quickly declines to 0, indicating that periodic vortex shedding has ceased. For the circular profile, this occurs at an L over D of around 2. However, for square and triangular profiles, vortex shedding ceases at approximately 3. Therefore, in order to prevent vortex shedding, square and triangular Bluff body profiles require splitter plates approximately 50% longer than Bluff bodies with circular profiles. This figure shows the maximum absolute value of the pressure magnitude during established flow as a function of splitter plate L over D. As is the case with the amplitude, the magnitude reaches a value near 0 for the circular profile at an L over D of 2, while the other profiles converge to a minimum value at 3. In the case of the square profile, the pressure magnitude, even when vortex shedding is ceased, is approximately an order of magnitude greater than those of the other profiles. The results of the CFD studies demonstrate that the Bluff body profile and the splitter plate L over D have a pronounced influence on the frequency of periodic vortex shedding. This figure shows the period of pressure fluctuations against splitter plate L over D. In all cases, the period slightly increases with splitter plate L over D. The circular and triangular profiles start at a period of approximately 4.6 seconds, while the square profile started with a period of around 5.9 seconds. This means that the square profile period is around 25% greater than the circle and triangular profiles. The periods increased approximately linear, with increased splitter plate L over D to 15 to 25% of the starting values. The goal of this effort was to compare the effect of bluff body profile on the ability of a splitter plate to prevent periodic vortex shedding. This goal was accomplished by creating CFD models of cylinders of circular, square, and isosceles triangular cross-section. These CFD solutions were solved as transient, laminar, incompressible, two-dimensional flows using OpenFOAM's piezo-foam solver. The cases included a splitter plate with a ratio of length to characteristic diameter of the bluff body of 0 to 4, and a Reynolds number equal to 100. Domain and mesh convergence studies were conducted to ensure that the solutions were accurate. The results of the simulation were inspected visually using Parafoam and post-processed with Excel. Pressure data was extracted at several probe points in the wake of the bluff body and used to evaluate the effectiveness of the splitter plate configurations. An FFT was also performed to determine the vortex shedding frequency of each configuration. The results showed that the bluff body profile and splitter plate L over D had a weak effect on the frequency of the pressure fluctuations. The pressure fluctuation period of the square profile was approximately 10% greater than the circular and triangular profiles. The period also varied by 15 to 25% between an L over D of 0 and 3. It was also found that the bluff body profile had a strong impact on the splitter plate L over D required to suppress periodic vortex shedding. The results showed that a circular cylinder only required a splitter plate with an L over D of 2. However, square and isosceles triangular cylinders needed splitter plates with an L over D value of 3. This represents a 50% increase. Additionally, even with periodic vortex shedding suppressed, the square cylinder exhibited downstream pressure drops of almost an order of magnitude greater than the circular and triangular cylinders. Therefore, it is apparent that the shape of a bluff body may have a noticeable effect on the length of a splitter plate required to suppress vortex shedding and other characteristics of the flow.